try to present you what was done in the task 5.2, which was precision genomic mating accounting for non-additive genomic effects. So first I will try to explain why we did what we do. So what do we think when we think about non-additive genomic effects? The natural answer will be heterosis and dominance, and that is why the task is at the beginning quite linked to to work package 4. But still, cross-breeding evaluation is an ongoing work, so we wanted to start to work on this task. So we choose to focus on alternative non-additive effects, such as gametic variance, which I will explain a bit later what it is. A link between gene of interest and breeding values, and also a correlation between traits. And what we thought that was the easiest way to start working on genomic mating plan, and was to simulate offspring in order to have at least one scenario with all the genotypes for animals and for offspring, and then try to implement some plan based on this simulation. Cannot move to the, yeah. Just to give you some background on gametic variance, I don't know how much you're familiar with this. So the idea is that when looking at the scheme, when you have an example with 4 animals and 2 chromosomes and a paternal and maternal haplotype for each chromosome. So you have L1, the locus 1, which is linked to L2, and L3, which is linked to L4. And if you assume that all locus have the same effect, so meaning that the locus in red has a +1 and locus in blue are -1, then all bulls are the same genetic values. They carry all 2 favorable alleles and 2 unfavorable alleles. But when you look at the possible gametes, there is various combination of gametes, meaning that bull A and bull C will have a gamete with 25% of the gamete will have a breeding value of 4, 25% of breeding value is -4, and 50% of 0, meaning that the variance will be around 10. But if you look at bull B and D, the haplotypes are mean of 0, meaning that 100% of the gametes will have a breeding value of 0, meaning leading to a gametic variance of 0. So why do we wanted to look at this gametic variance? Because Nair gametic variance mean Nair variance observed on offsprings, and what is the interest of more variance? To a breeding company's point of view, it will mean an increasing chance to get a top bull, but to a breeder point of view, it will also mean a higher chance to get disappointed, because you'll be very far from the mean, and you can be very far from the mean on a good way, meaning that we'll have a top bull when you expect another word, but don't remember. But when you expect a normal bull, I would say, but also you can have you can have less lower breeding values than what you were expecting from the mean. So we had two objectives in our study: to use the gametic variance in order to have first indicators, and to develop an indicator of gametic variance. So what we did at first, so we started from a simulation process. So what we did basically was to start with a list of bull and a list of dam. We simulate offspring from their genotypes. And then we just rerun a genomic evaluation, which was very similar to what we do routinely on genotypes, on real genotypes. So once you have the genotypes simulated for offspring, you just evaluate them. So you can have results on GEBV and also on genetic tests. And that's what you can just do basic statistics on these results and to see what is the mean, what is the variance, and also do specific analysis based on if you want to focus on specific gene of interest and stuff like that. So this part is already available for breeding companies. So that's what I just talk about. So the idea was to have statistics on viability of progeny. Then you can do statistics to get the number of offspring or the probability to have offspring above a certain threshold for entry, to compute statistics for specific gene conditions. For example, non-homozygous for genetic defect, to focus on red animals or less. And our goal was to optimize mating and to account for the gametic variant. And the idea was to prove to breeding companies that they can use maybe bull with a little lower genetic GEBV, but maybe with a higher gametic variant. So we hope that they will use a larger number of bull in order to achieve a top mating and have a top bull. Still, it's only a tool which can be used by breeding companies, but because you still need some luck and a lot of embryos to have the perfect bull out of 500 simulated offspring. But our idea was really to give breeding companies the same larger amount of information for progeny in order for them to choose the best mating. So the tool is already transferred to the French Evaluation Center from 1 year now. So 6 breeding companies are now using this tool in their scheme in 4 different breeds. So there is a really great interest in this tool in France. And 1 company is already using it to promote bull with homogeneous progenies. But as I discussed a bit later, previously, the simulation need a lot of computing time, because when you want to have all your bulls with all your females, it's quickly grow to a large number of offspring. So we had the computing time going from 40 to 100 hours, depending on the number of progeny simulated. So it cannot be used to plan mating on farm. So that's why we try to have a proxy to estimate gametic variance. So this is an ongoing work with in collaboration with INRAE and Didier Boischard. So we did a first test using a simulation based on 50 sires, 500 dams, and 500 offsprings. And we compute here the correlation between the variance observed in simulated progeny and the predicted gametic variance we computed and the parents. So in the table here, you'll have the correlation we obtained between the variance observed in progeny and the percentage of on the true indicator I just said. So what you'll see that the homozygous C is clearly not a good indicator because the correlation are quite low. Our first indicator is a little more promising, but still the results are lower than what we expected because you have correlation ranging from 0.3 to 2.6, so it's still quite low. So we need to improve the indicator, and that will maybe be done when finding the good balance between computing time and accuracy, because you need to be careful and check the number, how many SNP you want to take into account in our indicators. I just wanted to add a slide, meaning that we found, as other paper found, that there were no link between observed progeny variance and GEBV, and we did that on touch rate, so somatic cell score and protein yield in TrueBrit, Holstein, and Montbéliard. So what do we expect from our simulation tool is to directly compute probability to get a top bull from one mating. So breeding companies can focus on specific trait, on specific objective. You can get probability to compute, you have the possibility to compute one probability per breeding goal, and to select animal with specific characteristics if you want to focus on gene of interest. You can account for gametic variance when selecting sire and dam, and we want to do I don't know when, but we want to try to see if accounting for this gametic variance is very useful or not. So we plan to try some breeding scheme simulation based on both gametic variance and GEBV. And in another perspective, the breeding companies can also select the bulls with reduced gametic variance to limit risk for farmers. So there is still work needed to develop proxies in order to avoid the simulation and computing time. And in a sense, it means that our simulation wasn't useless because it will be used to validate our proxies. And that was, and now the question I had for the meeting was, do we go back? I guess the idea was that as long as we stick to an additive model, the expected GEBV of offspring was the mean of parents. When moving to a more complex model, this is no longer the case. So what can we do? Can we adjust the formula? So if we can include some dominance effect, but it means that we cannot include effect for all the SNP, but maybe we can have some focus on gene of interest or major gene when both parents are genotyped, and include it and adjust the GEBV of offspring. I don't know, I was just I wanted to stimulate the discussion, but I don't know. I just write down what I was thinking about, so it explains why it's a bit confused. But moving to crossbreeding, so again here we can add a component linked to heterosis, but it can become complex when sire and dam are already admixed animals. So the question was, is it worth to move towards a complex model in order to predict the value of offspring, and how can we do that?